All right, welcome everyone to 4.1, our first video of chapter 4. Like it says here, we're going to be arguing in this video that area under the curve actually has some real world value. In particular, if you have a velocity curve, it will yield displacement. And then with that, we can solve some various application problems. But this is kind of a motivational video to say that, hey, this area under the curve thing has value. And so I'd like to maybe illustrate this, do a quick reminder here, right, that probably from your favorite physics class or physical science class or what have you, you probably learned that if you have a nice constant rate, thinking about velocity and whatnot, a common formula to give is distance equals rate times time. So I just want to make sure that everyone remembers this. And so with that, I would like to showcase this example. Suppose a runner travels at 20 feet per second. And the question is, how far does she travel between t equals 1 and t equals 9 seconds? And I'm going to graph this out. So maybe if this is my time axis right here in seconds, we can go from 1 second here, and I'll just say over here maybe as 9 seconds. And then along my vertical axis, this will be the speed or the rate, and this is 20 feet per second. So I'm going to go ahead and maybe put up a 20 here. And again, this is in feet per second. And if we were to just use this formula, right, the amount of time that this runner was running is between, let's see, 1 to 9. If I subtract that, that's going to be an 8-second window. And so that's the time that they were running, and they had a rate of 20 feet per second. So if I want the distance here, that would be 20 feet per second times the 8 seconds that they were running. And we can see that the units work out very nicely where they cancel, and we're left with 160 feet. So that would be how far this runner travels. And so I'd like to go ahead and showcase that this actually has something to do with area under curve. So if I was to draw, again, a nice constant velocity, so they are always at 20 feet per second, it would look something like this. And I'm going to go ahead and maybe just draw these dotted lines down here between 1 and 9. And so this right here is a rectangle. I'll shade it in. It has a height of 20. Oops. And it has a width of 8. So if you asked, right, what is the area of this rectangle? And I mean, the units and everything would come along just like they did in the equation over here as well, right? 8 seconds and 20 feet per second. That if you were to multiply those together in order to get the area, right, you would get the same result of 160 feet. And so that showcases, right, that this area under this curve here is actually giving us this incredibly useful quantity. That is the displacement, or right, how far this runner traveled. Now, of course, in the real world, it's unlikely that you ever have, a constant velocity. I mean, especially with a runner or what have you, right? This is going to be changing. And so here is something that's a little bit more accurate. But you can see that it's also more challenging, because if I want the area under this curve, and again, I'm doing this from t equals 1 second to t equals 9 seconds, so from 1 to 9 here, I'm interested in this area. If I'm interested in how far did they travel. And right, I mean, last time it was a rectangle, and so I knew a geometric formula for area of a rectangle. But here, this is not a nice geometric shape, right? There's a lot of curves and whatnot. It's not a circle, it's not a triangle and whatnot. So this is hard to get the exact answer for. Um, However, we can at least approximate this, and we're going to approximate it with rectangles. And you'll see why we do this here a little bit later in chapter 4. But I'm going to start off by approximating this runner's distance that they travel between t equals 1 and t equals 9 seconds using 4 equal width rectangles. Sketch the area on the graph above. So, okay, if I want 4 equal width rectangles and I have a total width of 8 seconds, let's go ahead and break this in half. And that would be 2 equal width rectangles. And let's break it in half one more time. And that's going to give us 4. So it looks like my rectangles go from maybe 1 to 3 seconds, then from 3 to 5, then from 5 to 7, and 7 to 9 lastly. Now I need to figure out, okay, what should the heights of these be? And I mean, I want them to definitely go along with this velocity curve here, but you can see that there's multiple heights that I could reasonably choose, right? For instance, if I just think about from 1 to 3 seconds here, I could choose the height over here on the left-hand side and decide that this is the height of my rectangle here. I could choose the height on the right-hand side and say I'm going to choose this as the height of my rectangle. I could choose maybe right in the middle, right? And that I want to be the height of my rectangle, right? So there's a fair amount of options, and these all have different names, which we'll be giving to them a little bit later in this section. For right now, I'm going to go ahead and just choose the right-hand endpoint and always use that to be the height of my rectangle. But this is just an estimate, and right, other people can estimate this slightly differently. And so, okay, we'll go ahead and choose that as the height for my first rectangle. For my second rectangle, again, I'm going to choose the right-hand endpoint, something like that. There's my third rectangle here. And finally, my fourth rectangle. So we can see that this first rectangle here, the area of this is going to be a little bit less than the area under the curve. For this next one, it looks like maybe it's a little bit more. It's pretty close. For this third one, it looks like it's certainly more. And then for our last one, right, our area here is a little bit too much. So if anything, this is probably going to be an overestimate for how far the runner went. So let's go ahead and calculate out this area. So again, each rectangle has a width of 2, so 2 times. And my first rectangle here, I think that height is about 5.1. That's what I'll use. My second rectangle, again, a width of 2 and a height, again, pretty close to 5.1, we'll say. Next up, my third rectangle, width of 2, height of, I don't know, we'll say 5.9. And then finally, my last rectangle here, we have a width of 2 and a height of, we'll say 7.5. So let's see, the total area is going to be, let's see, 10.2 plus 10.2 plus 11.8 plus, oh, I forgot my decimal point there. 2 times 7.5 is going to be 15. So when I add these all together, and you can use a calculator for this, right? I'm going to get 47.2. And assuming that our units all stayed the same, and this was velocity in feet per second, and these were seconds, right? Then this would be feet here. So this is the distance that this runner traveled between t equals 1 and t equals 9 seconds. Again, this is an estimate. We think probably that it's an overestimate because our green area was a little bit bigger than our blue area, but it's a good approximation. And of course, we could do even better than this. So again, I hope that this illustrates that the area under the curve actually has physical meaning associated with it. And so this is a worthwhile thing to study. Let's go ahead and try our last problem. We had a nice picture given to us. I want to showcase that you can also do this even if a picture is not given to you. And so suppose the velocity is given by this equation, square root of t, and this time it's meters per second. Approximate the distance the runner traveled from t equals 0 to t equals 4 seconds. And we're going to use time intervals of 1 second and have the graph touch the left-hand side of each rectangle. So this is going to be called a left-hand sum. So I'm going to go ahead, even though a graph was not given to me, of course, one option that I have is that I could choose to make a graph. So I'm going to go ahead and make a graph here. Do something like that. And we'll have at time 1, I know the square root of 1 is 1. And I know the square root of 4 out here is going to be 2. And of course, we could go ahead and include here 2 and 3. Just to mark, but I don't know what the nice values are for square root of 2 or square root of 3, but we can go ahead and plug those into our calculator and get some result there if we wanted. All right, so we have a good sketch. We're going to be approximating the area here under this, good, because that would give us the distance. And this says to use time intervals of 1 second. So my first rectangle would be from 0 to 1. My second rectangle would be from 1 to 2. My third rectangle would be from 2 to 3. And my fourth and final rectangle would be from 3 to 4, because again, it said from t equals 0 to t equals 4 up here. So that's time intervals of 1 second. Now, I would like my rectangles that I choose to touch the left-hand side on the graph. So for my first one, it looks like it touches on the left-hand side over here at 0, at a height of 0. So that's not very interesting. For my second rectangle, it looks like it touches on the left-hand side over here. So that's going to be square root of 1 is 1. And so let me go ahead and draw in my full rectangle. The width and the height is going to touch on the left-hand side here. My third rectangle is going to go ahead up here, and again, it's going to touch on the left-hand side. So we're going to go over like this. And then my fourth and final rectangle, again, touching on the left-hand side. This will be the height. And if I'd like to, I can go ahead and shade this in. Oops. All right. So now we can do our calculation. So the area of the first rectangle, well, it has a height of 0 and a width of 1. So not very exciting there. My second rectangle would have a height of square root of 1 and a width of 1. My third rectangle has a height of, and again, it touches over here at 2, and this is the square root function, so its height's given by the square root of, in this case, 2. So height of square root of 2, and again, the width is 1. And then finally, my fourth rectangle has a height of the square root of 3, because again, it touches on the left-hand side, and a width of 1. Now, in this case, multiplying by 1 doesn't do a whole lot. So we're going to have 0 plus 1 plus root 2 plus root 3. And if we go ahead and we plug this into our calculator, right, we're going to get around 4.146, we'll say, meters. Because again, this is in meters per second this time. Okay, moving on. Our next question is your answer from A an underestimate or an overestimate? Explain. So looking at, again, we were trying to approximate the area under this square root function. I originally had shaded that in green, and then these rectangles that I included here in purple, right, we can see that they didn't really cover up all of the green area. And so if anything, this seems like we're missing some of the area that wasn't really accounted for. And again, you can see that here, a little bit here, certainly some here, and some here. So there's some area that wasn't accounted for. So our purple area that we calculated here, this is going to be an underestimate. So let's go ahead and write that out. The purple, this was the estimate. Area is less than the green. This was the true area. So it is an underestimate. So I think that the runner went around 4.146 meters, but this is going to be a little bit less, right? The true value is going to be larger than that. And so my final question is there a way to get my answer here from B without using a picture or a graph? And the answer is yes. If you want to pause the video and think about it, you certainly can do that, but it does rely on some properties of the graph. All right, so I'm going to go ahead and spoil the surprise. And the main thing here is that the function, the square root function, is an increasing function. And so because it is an increasing function, we know that if we choose values on the left-hand side, well, this is where the smaller values are, right? If I was to choose on the right-hand side, for instance, this is where the larger values are. And so because this is an increasing function and we're always choosing on the left-hand side each time, the values are only going to get bigger from there on that interval. And so we know that this has to be an underestimate because of that. So it really has to do with the fact that it's an increasing function. So since the graph, and I'll just say yes, maybe since the graph is increasing, And since we are using a left hand sum, this means on the left, it will always be a smaller function value, say, and will only go up from there. So it will be an underestimate. So yeah, we don't need the graph here, but it is nice just to be able to look at this and kind of verify that what our work is doing for us. All right, well, that is a good place to end it for right now. I'll see you in the next video.